Yeah, all right, we're going. So 2.6, the chain rule. So as I mentioned, this little link of chain here kind of looks like what the chain rule is going to end up looking like. Something times something times something times something. And the word chain also comes into play when you think about chain reaction. So you've already recognized this as the Rube Goldberg machine. What happens here is you do something here at A. You turn the crank at A, and A is going to affect everything in sequence, but ultimately it's going to affect P. This thing rickets down here and traps the little mouse at the bottom. So ultimately, changing A changes P, but by way of all these other intermediate chain reactions. So if you were to express the game of mousetrap in Leibniz notation, here's what it would be. Doing something to the independent variable A will have an effect ultimately on P, but it'll affect it this way. A is going to affect B. B then in turn affects C. C does something to D. D affects E. E has a profound influence on F. F changes G's life forever, so on and so forth. Okay, all the way down until N affects O, and O finally affects P. So this is what it looks like in Leibniz notation, and it's equivalent to dPdA, you can kind of see, because notice your dBs divide out, your dCs divide out, dd's, these divide out all the way down until you're just left with dP over dA. So the chain rule is kind of like a chain reaction. It's a chain reaction of derivatives, really. Here are some of the things we can currently do without the chain rule. We could find the derivative of these four functions, x squared minus 1, boring, sine of x, boring, 3x minus 2, boring, and x minus tangent of x, boring. We could do those today. With the chain rule, though, we could find the derivatives of these four dudes. Much more exciting. Y equals the square root of the quantity x squared minus 1, sine of the quantity 5x, the quantity 3x minus 2 squared, and x minus tangent of the quantity x squared. What did all those have in common that these did not have? I said the word what in each of those? Quantity. Yes, quantity. I'm going to replace the word quantity with blob. Are you all okay with that? The square root of blob, sine of blob, blob to the 7th, and x minus tangent of blob. So anytime I say blob or quantity, it's because the thing is something more than just a plain old x. These functions all are then considered some type of composite function. Yeah. When you have one function embedded inside of another function, you have a composite function. So what the chain rule allows us to do is it allows us to take the derivative of what type of functions? Composite functions. Now we have to identify the inside blob and the outside blob. Okay, so here's the chain rule. We're going to list it two ways. If y equals f of u, that means y is a function of u, and u is equal to g of x, u is a function of x, then if you're trying to find the derivative of y with respect to x, you could find the derivative of y with respect to its variable u, and then find the derivative of u with respect to its variable x, and then multiply the results together. And why does that work? The du's essentially divide out, and you're left with dy over dx. So there it is in Leibniz notation. But here is a little bit nicer way to think about it. If this is truly a composite function, then let's just write it as f of g of x, where g of x is your inside function, and f of x is your outside function. So you're going to take the derivative like you would peel an onion, with lots of tears. No, not with lots of tears. From the outside in. You peel an onion from the outside in, okay? And you peel one layer, like, hey, there's another layer, and you peel the next layer, okay? This is assuming that you're peeling onions and not chopping them up. So that's what we're going to do with the derivative. We're going to take the derivative from the outside in. So this is f of blob. What is the derivative of f of blob? F prime of the blob times. So this is the multiplication part. Times. Now you go inside where you have the blob, and you multiply by the derivative of the next layer. What's the derivative of g? G prime. Now, if you want, you could even think of g of x as having an inside function. This has an inner inside blob. It's x times, what's the derivative of x? 1. So if you ever take the derivative of a composite function, you want to write it so you can see the layers. All you have to do is take the derivative of one layer at a time. It's like unpacking boxes. We do the outside box first, and then inside there's some more contents. We take it out, and we keep taking it out until we get to the end. And you're doing what with all of your derivatives? What operation? Multiplying them together. You're not adding them, you're multiplying them. It's a chain link. Chain's a little bit stronger. So you need a spot weld, like a multiplication dot instead of a plus sign. Now, it's also good to take inventory. Notice, really, you have two non-trivial functions. X by itself is a trivial function. But you have an outside function f and an inside function g. So with two functions embedded inside of each other, you should end up with two non-trivial factors. If you had f of g of h of x, if you had 3 layers on your function, guess how many factors you're going to have in your derivative? 3. So it's kind of like the product rule where the number of factors ends up equaling the number of terms. Here, the number of layers ends up equaling the number of factors. So let's try it out. Example 1, the derivative with respect to x of that. Well, step 1 is to simplify, rewrite it. The square root of x squared minus 1, is that just x minus 1? Yes or no? No, don't do that. That's not correct. You can't just take the square root of each. But what you can do is say that it's x squared minus 1 all to the what power? 1/2. So now you have 2 layers. You have the outside layer, blob to the 1/2, and the inside layer, blob, which is x squared minus 1. So with 2 layers, you're going to have 2 factors in your derivative. We work from the outside in. What would the derivative of blob to the 1/2 be? By the power rule? 1/2 blob to the negative 1/2. That's the power rule. We don't take the derivative of everything at once. Everything has its own factor. So we just rewrite the blob. 1/2 blob to the negative 1/2. Times. Now we go inside and we're like, hey, what's happening? Blob, x squared minus 1. We'll multiply by its derivative now, which is 2x. And there you go. You got the purple layer and you got the blue layer. Blob to the 1/2 becomes 1/2 blob to the negative 1/2 times the derivative of x squared minus 1 is 2x. And that's it. Now you've done with the calculus, you just clean it up a little bit. And things do happen nicely here. The 1/2 and the 2 divide out. You're left with an x in the top. And if you clean up that other factor, you're left with the square root of x squared minus 1. So there it is. That is the derivative of the square root of x squared minus 1. Chain rule, composite function. 2 layers, 2 factors. All right, letter B. The derivative with respect to x of sine of 5x. How many layers do we have here? 2. Now, sometimes adding parentheses where they're not needed can help you see the layers. So anytime you have something more than just plain old trivial x, it needs to be considered as its own separate function. So I have the outside function is sine of blob, and the inside function is 5x. So I take the derivative from the outside in. The derivative of sine is what? Cosine. So cosine of blob, and then times the derivative of the inside layer. What's the derivative of 5x? 5. And now you just rewrite that as 5 cosine of 5x, and you don't need the parentheses anymore. Chain rule. Kind of fun. Every time you multiply by another factor, it should be a little bit smaller than the one that preceded it. Okay, because you're unpacking boxes, and the first box has to be the biggest if it's going to contain all the other boxes. All right, let's look at this one here. 3x minus 2 to the 7th power. You sure don't need the chain rule to take the derivative of this one. You could expand it out, right? Write it side by side 7 times and FOIL it out and combine like terms and use the power rule. But the person that's trying to do that, they haven't even really finished the first expansion by the time we're done. Because for us, it's just blob to the 7th. And the derivative of blob to the 7th is 7 blob to the 6th times the chain rule, the derivative of the blob, which is 3. And we're done with the calculus, really. 2 layers, 2 factors. And, of course, now you can combine it. 7 times 3 is 21. 3x minus 2 to the 6th. So you're essentially done cleaning up before the other person has really even expanded maybe one of them times itself. Much less after he finishes taking the derivative, he's going to have to try and factor it again. Oh, my gosh. Loser. Whoever's doing that, right? Whoever doesn't know the chain rule. Now, if you were to set this up using the limit definition of the derivative, you'd have to use a mighty big sledgehammer, right? Thank goodness we don't have to do that. We got the chain rule now. All right, letter D. It's x minus tangent of x squared. What are we actually squaring on that last term? the x, right? So again, adding grouping symbols. So this one is not a chain rule to start with. This is just the derivative of one term times the derivative of the other term, or minus the derivative of the other term. So the derivative of x is 1 minus, and now it's only in the second term that we have a chain rule. Tangent of blob. What's the derivative of tangent of blob? Secant squared of the same blob. And in that term only, times the derivative of the blob, which is what? 2x. So that 2x does not get multiplied by both terms. You have to unpack the boxes in each separate term as you get to them. So the simplified version is 1 minus 2x secant squared of x squared. You can bring that to the front of this term only. Kind of nifty. All right, 1 over x plus 1. Why is this guy here? We don't need the chain rule for that. We have the what rule? We have the quotient rule. We have the Hody-High rule. Can we use the Hody-High rule? Sure. What's d high going to be? 0. So there's a quicker way to do it. If you ever have a quotient and your numerator is a constant, any constant, the Hody-High rule will work, but it's going to be a little bit faster if you rewrite it as the constant times the denominator to the negative first power. It's just going to work a little bit faster. And now I can't expand something to the negative first power, but I don't need to, because I have blob to the negative first power, and I can use the chain rule. So what's the derivative of blob to the negative first? Negative blob to the negative second, and I'll just put that x plus 1 in there, times the chain rule, the derivative of x plus 1, which is what? 1. Now notice if you needed a second derivative, it's all ready to go. Negative 2 times negative 1. Third derivative, so on and so forth. So especially for higher order derivatives, if the numerator is a quotient or the numerator is a constant, then you don't have to use the quotient rule. Now cleaning this up, we're left with negative 1 over x plus 1 squared. Then you get the same answer if you did the Hody-High rule. Just a little bit faster, less risk of making careless mistakes if you can write it and use the chain rule. All right, this one here, sine squared of 3x. What are we squaring? The sine. So whenever you have something that's written in this condensed notation, it's probably a good idea to write it in expanded notation. So I'm going to show colors here. Blob squared ends up being the outside layer. Next you have, inside the blob squared, you have sine of blob. And then the innermost blob is going to be 3x. So how many layers do we have here now? 3, right? We have 3. Blob squared, sine of blob, and then the innermost blob, the blobbiest of all blobs, is 3x. So with 3 layers, how many factors are we going to have? 3, right? From the outside in. Blob squared becomes 2 blob to the first. And then you can just use the same color and write the inside function. That's fine. Times. Now we go inside a layer and we're at the orange layer. Times the derivative of sine of blob, which is what? Cosine of the blob. And then times the derivative of the innermost blob, the derivative of 3x is 3. Yeah. So you're done with the calculus. Now if you want to clean it up, you could call it 6 times sine of 3x times cosine of 3x. You could do that. Or, what is 2 sine times cosine equal to? Remember the double angle identity? Sine of 2x is equal to 2 sine x cosine x. That's kind of what we have here. We have 2 sine of 3x cosine of 3x. So we can condense that to sine of twice 3x, which would be sine of 6x times the 3 that's in the back that doesn't get used. Remember the double angle identity. As long as it's 2 sine of blob cosine blob, it's equal to sine of twice the blob. So it becomes sine of 6x times the 3. So that might be something I would do on a multiple choice to get you to do one thing extra at the end. It's also a little bit easier because it's less typing. All right, I think we're going to stop there for the day because I don't think if we start any of the bottom line we're going to finish because they're a little bit beefier. But there you go. You got a good start on the chain rule, and you could do a lot of the problems then from the worksheet. But first things first, particle motion worksheet due tomorrow, little quiz tomorrow, and then we'll keep moving on into the chain rule.